Good morning. This presentation is about RF SOI MOS and switch modeling. This is the outline of this presentation. The main purpose is to explain what are the key elements for successful RF switch modeling. First, we need to correctly choose the right model for that purpose. Next, we need excellent small signal model. I will then talk about the large signal modeling and what is required to obtain such accurate large signal model. Then I will give a few words about substrate and box modeling, possibly including nonlinearities. And then I will detail the verification of the large signals and the harmonics and IMD under realistic switch structures. Let us start with an introduction. On the left, you have a sketch about a front-end module for long-term evolution for mobile communications. As you can see in this diagram, we have a lot of switch required to connect the antenna to the power amplifiers for various bandwidth. On the right, you have an example of a simple single-pole double-throw switch and how it can be implemented with the transistors. With SOI, it is possible to stack the low voltage MOS in order to withstand larger voltage, typically up to 20 or 30 volts if you stack about 10 devices. So this is a nice way to realize a switch. Also, SOI allows minimizing the crosstalk and the losses. So in the end, if you look at this table with the figure of merits for RF switch for various technologies, you will see that SOI CMOS is a competitive technology to realize RF switch at a lower price. These are the important figure of merits for RF switches. First, we have figure of merits based on small signal, like insertion loss and isolation. But also large signal figure of merits are important. For instance, for high power handling, it is required to have a high P1 dB. Also, the switch must introduce low distortion, so low harmonic contents is required. On the upper left, you have a diagram of an RF switch connecting a receiver and an antenna. In this diagram, we can see that the transmission signal can be coupled with a possible jammer received at the antenna and create intermodulation distortions, possibly being in the bandwidth of the received channel, which is very detrimental to the overall performance of the system. So it's important to have high immunity to jamming signals and therefore low IMD in the switch. So as you can see, the important figure of merits for F switches are related to small signal but also large signal aspects. This is why harmonics are very important. Let us go back to the outline, and now we are going to discuss how to choose the right model for RF switch modeling. Here you have comparisons between simulations with the PSP model on the left and BSIM4 on the right. The output power as a function of the input power is plotted for various harmonics from the first to the fifth harmonic. And as it can be seen, only the PSP model is able to reproduce the theoretical slopes that each harmonics must have. The BSIM4 therefore cannot predict harmonic behavior, and it is not suitable for RF switches modeling. We need excellent small signal model in order to build our RF switch model. And in order to do that, it's important to have excellent test structure layout. RF test structures layout is extremely complex. It has to be done by highly skilled engineers who are fully aware of the embedding procedures. RF test structures cannot be left to inexperienced layout engineers, because there are many common flaws and mistakes which can compromise the RF measurements accuracy. Erroneous measurements can be distinguished from accurate measurements when errors are originating from test structure layout. The problem with the erroneous test structures layout is that they will produce some bias in the measurements. And the systematic bias can look very similar to accurate measurements. And this is a problem because the model can still feed the measured data, but the model will then not reflect the actual device. In order to exemplify the risk of obtaining poorly designed structures, I'm going to present now some common mistakes when making layout of RF GSG test structures. Here we have RF GSG test structures with the signal pads which have a too large area. Actually, the capacitance of these pads can be up to 72 femtofarads, while an optimized pad can have a capacitance down to 20 femtofarads. This can look like a small difference, but actually a small error in the measurements of this pad can lead to a large error in the measured capacitance of the intrinsic device, especially when measuring CGS as low as 1 or 2 femtofarads. This effect is usually confirmed by measurements. For instance, when you extract the CGD capacitance from S parameters between port 1 and port 2, it's always more accurate than when you extract CGS capacitance between port 1 and the ground. Another very common mistake is to have too long connection lines. Actually here, on the zoom on the RF structures, it can be seen that the access line to the source is very long and narrow, which constitutes inductance. In this case, the open short deembedding assumption fails, and it's not possible to apply a correct deembedding to these structures. This results in inaccurate S parameters of the measured transistor. Another common mistake is to have a different connection for the body and for the source. In this case, this will result in erroneous short dummy structures, because then the short structure will not be consistent with the device, and this will lead again to inaccurate measurements after deembedding. Here is another example of poorly designed structure. Here, this is a zoom layout of a multi-finger transistor. As it can be seen, it has two gate contacts on the left and on the right. On the left, you can see that there are not enough vias to connect the poly of the gate. This means that the via resistance will be at the same order of magnitude than the gate resistance of the transistors, which will strongly degrade the maximum oscillation frequency of that transistor. Also, as it can be observed, the two gate contacts are linked by a long and narrow metal wire, which will have an inductive behavior. This is not good because the gate resistance of this transistor will suffer from distributed effects. As we have seen, there is a whole list of errors, flaws and mistakes which have to be avoided to ensure accurate RF measurements. We need to measure the actual intrinsic devices, not lay out parasitic effects of poorly designed TEGs. Let us see now an example of an optimized GSG RF structures. You have the top view of the whole structure on the left. This is only half of the structures because the ground pads are shared between one structure and the other. The top metal is the yellow color, while the other colors corresponds to other metal layers. As you can see, the signal pads have been optimized and the area has been minimized in order to minimize the capacitance associated with these pads. Also, the whole structures complies with JRC density requirements. That means that no random dummy filling or chiseling is required, and no extra parasitics will be generated during the silicon implementation. You see the various sheets composing these structures, with the top metal, the intermediate metals, and the metal 1 layer. The metal 1 ground shields avoids a direct substrate coupling, and also it provides a more ideal behavior under high frequency. The intermediate metals allow a clear DUT reference plane. Any connections to the source body to the ground is in place. This is an example of the layout of a full RF test chip for SOI process. This is a complete DC and RF test chip design and layout, from concept to fully validated DRC clean layout. This was an outsourcing project from a foundry. The test chip was designed from scratch for a new 0.13 RF SOI process. Let us have a look at the outline. So now, in order to obtain an excellent small signal model, we need accurate de-embedding and a consistent de-embedding with the test structure layout, of course. After calibration of the VNA, the reference plane of the measurements is located at the center of the RF pads, as it can be seen on this sketch. All the parasitics associated with the pads and access lines are still included in the measurements, so this means that they have to be removed. The operation consisting in removing these parasitics is called de-embedding. After de-embedding, the new DUT reference plane will be at the center, as exemplified by the box dashed lines here. Regarding de-embedding, the industry standard is the open short de-embedding. In order to apply such de-embedding, you need an open and a short dummy structure. The assumption to realize this de-embedding is that part parasitics are modeled by parallel conductances and series impedances only. If this is not the case, open short de-embedding cannot be applied. Here is a representation of the operations required to perform this open short de-embedding. First, the parasitic capacitances are removed by the subtraction of the Y parameter matrix of the open. Next, the short is also de-embedded by the same methodology from the open. In the end, all these parameters are converted to the matrix, and the subtraction of the DUT and of the short will lead to the intrinsic device, the matrix, which can now be converted again to S parameters. Let us see the implication of the layout of these open and short dummy structures. You have here a sketch of GSG RF structures, where we show only half of the structure for simplicity. You can see the ground and the signal pads, and in the center a sketch of a MOS transistor. You have here the examples of an open dummy and a short dummy designed at the top metal level. This means that the DUT reference plane is now defined at the top metal. On the opposite, you can also design your open and short at the down to metal 1. This will mean that the DUT reference plane will now be located at the metal 1. Of course, the advantage of these structures is that you can remove more parasitics, but the point is that its design is very challenging because its behavior will be non-ideal at higher frequencies. So the test structure layout actually defines the DUT reference planes. That means that it will define which parasitics are part of the models. And it will also define the upper frequency limit for your measurements. Depending whether you choose the reference plane at metal 6, at metal 4, or at metal 1, your open and short structures will have more or less ideal behavior. And this will define the maximum frequency at which the assumption 1 defined before is true. So this will define the frequency range for which your de-embedding is accurate. Let us see an example of the measurement of an open dummy down to metal 1. At high frequency, as it can be observed from the graph, the capacitance starts to deviate from the ideal behavior. That means that the assumption 1 that we have stated before, pad parasitics are modeled by parallel conductances and series impedances only, is not true anymore. This means that when the measurement starts to deviate from the ideal behavior for the open short de-embedding cannot be applied.